Hello everybody. In this video we're going to talk about one new topic, which is the determination of the optimum pipe diameter. And this is one kind of famous problem that we usually discuss in fluid mechanics when we talk about the optimization. And this is like one very famous optimization problem. This is something that we're going to solve using Microsoft Excel, and hopefully I'm going to do this using MATLAB as well. But before we go through the calculations in the software, I would like first to keep this video as a refreshment to the information and a quick revision so that we can be all on the same page when we go to the software. So I'm gonna revise quickly the main equations and the main points that will be important in the solution that we're gonna go through in the next video or two. I'm gonna start first by the main equation that's gonna be used in this problem, which is the Bernoulli equation, or the modified Bernoulli equation actually. So Bernoulli equation, as all of us know, is a conservation of energy equation. It says that the energy is conserved for a fluid flowing from point 1 to point 2. So these are 2 points where the flow is going from 1 to 2. And it says that the energy has different forms. The original Bernoulli equation does not have this term and this term. It only has these three terms here and these three terms here, and it's used based on some assumptions that the flow is continuous, that there is a streamline, and the flow is non-compressible, and the flow is inviscid. Inviscid means that there are no viscous forces in the fluid, that there are no losses due to the friction between the fluid and the layers of the fluid and itself, and between the fluid and the pipe that is flowing in. So it says that the forms of energy that we have are these three forms: the pressure, the kinetic energy, and the potential energy. And this equation has the units of length. It's gonna be meter or foot or whatever unit, but it's a length form. And it says that the energy is conserved so that the pressure energy, potential energy, and kinetic energy at point 1, assuming I'm talking about the original Bernoulli equation that does not have this term and this term, is gonna be equal to the energy, or the summation of energies in the second point. So the whole energy is constant, but the forms may vary. So in case I increase the velocity by decreasing the cross-sectional area, then we will see that the pressure will increase. So if V1 is smaller than V2, then P2 is bigger than V1. So this is, I mean, smaller than P1. P2 is smaller than P1. So this is kind of the conservation of energy. But this is not the case in all of the cases actually, because the assumption that the flow is inviscid is not a valid assumption, because there will be some friction between the fluid and the pipes, and between the flow, the layers of the fluid while it's flowing. And that's why this term showed up, which is the losses term, and it takes into consideration the energy losses due to the friction and the viscosity of the fluid. And it's calculated from a very famous equation, which is this: F multiplied by L over D multiplied by V square over 2G, where L is the length of the fluid, the pipe, I'm sorry, and D is the diameter of the pipe. The V is the velocity, and G is the gravitational acceleration. This 9.81 meter per second square. So this is kind of very known equation, and the F is the friction factor, and we will go through this in the next slide or two. What I want to highlight here is that where the diameter shows up in this equation, because the aim of what I'm doing is to do optimization on the pipe diameter. So I need to understand where the diameter is showing up in this equation. So here's the first place where we will see the diameter. It's explicitly shown as diameter here. And we will see later here and here that there are some terms else that will have diameter in. But before I go through the places where we have the diameter, I want to like talk about this HP. It's the energy in case of, or added to the fluid in case of having a pump or a compressor or something like this. So it's adding energy to the fluid, so it has to be taken into consideration as well. This equation with the HP and HL are, or is called the modified Bernoulli equation. So it's the Bernoulli equation with the addition of two terms to take into account the energy added by the pump and the energy consumed or lost due to the friction and the viscous forces. Anyway, so back to the diameter. The velocities here are calculated from the flow rate and the area. And the area is, and it's calculated from V equals Q over A, which is kind of known thing. And A is pi over 4 d squared. So we'll see that the diameter shows up here in the velocity term, and it shows up here in the HL term. So we can see it here, and it's here as well because the velocity is here as well. So we can see velocity here, here, and here. Now let's talk more about the friction factor, which is the F. It's calculated from or based on the flow regime. So in case of laminar flow, they will see that Reynolds number is smaller than 2100s. Then it's going to be only function of Reynolds number according to this equation, which is 64 over Reynolds. So F is kind of has a linear relation with 1 over Reynolds for the range of laminar flow. And Reynolds number is known to be rho Vd over mu. So the diameter is going to be here as well in the velocity and in the diameter, which is explicitly in the Reynolds number equation. For the turbulent flow, it's going to be different. The Reynolds number is higher, and in this case, we will have the friction factor as a function of Reynolds number and epsilon over d. Epsilon is the roughness of the surface. So this is like when we have a surface, there are some irregularities on the surface, and this make, as we see here, more losses when the fluid is flowing beside the walls, and this creates more losses. So the epsilon is the length of, or the height of these irregularities, or of the roughness of the surface. Um, so we'll see that the diameter is also here in this term. So diameter is almost in like half of the terms that we have in Bernoulli equation. And it's there in different ways, either in Reynolds number, or either in the epsilon over d, or in the velocity, or in the diameter as it was in the friction factor or the losses equation. One thing else is that because the friction factor is kind of important thing and we use it a lot, there is this equation that we can use to calculate the friction factor. It's not like a friendly equation because you cannot calculate the friction factor directly. It has to be calculated by iterative solution. And I think we went through this in a previous video when we were talking about the solution of nonlinear equations in Excel or MATLAB. And we gave this as an equation or an example of a nonlinear equation. And we saw how we can calculate the friction factor from this equation. Anyways, this is something that we will use in one of the steps when we will do the optimum, or do the optimum calculations, or the calculation of the optimum diameter of the pipe. But we will go through this later. For the epsilon, which is the roughness of the surface, we can find it in tables, and it's function of the material that we're using to construct the pipe from. There are some materials that are pretty rough, such as the concrete. We know concrete is rough. You can feel the roughness by your hand. In the wood, you can feel the roughness. And here you can see that the values of the roughness are calculated in millimeters or in feet. So in the millimeters, you'll see that it's not small. It might be few millimeters in case of concrete. In some cases like glass, you'd see that it's perfectly smooth, so you can assume that or you can put the friction factor as 0, so will have no friction losses in this case. Or no, you will have some losses, but they're not due to the friction. They're going to be due to the Reynolds number, or the friction between the layers of the fluid by themselves, but not with the walls of the pipe. Anyways, this is something that we can find in tables, so it's not a hard thing to find. For the friction factor, we use this chart in many cases to calculate the friction factor. Here we have different values of epsilon over d, and this is the region between or where the turbulent flow starts at 4,000, and this is the region where the laminar flow ends, which is the smaller than 2100s. This is the linear relation between friction factor and 1 over Reynolds, and this is the function of epsilon over d and Reynolds number. So for each one of these lines, it's in an epsilon over d, and you see that it like has a big range from 0.00001 to 0.05, and we have here a range for the friction factor from 0.01 to 0.1, or maybe less than 0.01. So we can use this chart, or we can use the equation to calculate the friction factor. Now let's go to the pipes and talk more about them. So how do we choose the diameter of the pipe? Do we choose any diameter, or there are some standards? So this is something that's kind of well known, and the pipes are being used for like tens and hundreds of years, and that's why there are some standard diameters of the pipes that we can pick from. You cannot pick any random diameter, you have to pick one of the standard diameters. The pipe can be like defined using the inner diameter, the outer diameter, and the thickness, but what is available is something that's none of them. It's the nominal diameter. It's not the inner, neither the outer diameter. It's like one other diameter, and from this nominal diameter you can know the outer diameter of the pipe, and using something else, which is, or another parameter, which is the schedule number, you can find the inner diameter of the pipe. The relation, or you can know the thickness, and from the thickness you can get the inner diameter of the pipe, and you can see from here, this is a cross section of the pipe, this is the outer diameter, and this is the inner diameter, and this hashed part is the thickness of the pipe. So from this you can see that the outer diameter equals the inner diameter plus twice the thickness. This is thickness from this side and thickness from this side, so it's plus twice the thickness. So from the outer diameter and the thickness, we can easily calculate the inner diameter, and from the inner diameter you can calculate the area, which is pi over 4 inner diameter power 2. This is an example of tables where we can find the like all the data that we need. So from this nominal diameter you can find the outside diameter, and from the outside diameter for each nominal diameter you can pick one of the schedule numbers. For each schedule number it tells you the thickness in inches. So from this diameter and from this thickness you can know the inner diameter, and from this you can calculate the cross-sectional area. So this is how we can pick the diameter based on, or know the dimensions, the inner and the outer diameters, based on the nominal diameter and the thickness of the wall. Now let's go to the calculation of the optimum diameter, or the determination of optimum diameter. So from what we said, you can see that we can use different diameters, and these diameters will be fine. You can have the fluid flowing through the pipe, and it's working nicely. There are no problems, and you're putting a pump to push the flow, and everything is fine. But you can do calculations to pick the optimum diameter, which means that it's gonna be more economic. And this is the point, that there are many diameters that will be fine and they're gonna do the job without any problems, but one of them will be the most economic, so it's not gonna be costing more than any other diameters. So the cost that we are talking about can be separated into two parts. One of them is the fixed cost. The fixed cost is the cost of the materials that you are purchasing in the beginning of the project. So it's the pipes, the fittings, the pumps, the insulations, and anything that you pay for in the very beginning before you start the project. And of course, it can include the installation and any thing that is related to that. The operating cost is the cost of pumping, or the electricity that you pay for, so that you can run the pumps that will run or push the flow from the beginning to the end of the pipe. You can add some other things like the maintenance or any expenses that you pay in the lifetime of the project. So these are the two types of costs that we are gonna consider when we try to find the optimum diameter of the pipe. So it's important for us to understand how the diameter affects both costs. So from the logical perspective, you know that, or we can expect that if you use larger diameter, you have to pay more, and if you use smaller diameters, you have to pay less. This is like a logical thing because of the material that you are putting in the small pipe is smaller than the material you are putting on the large diameter pipe, and that's why you have to pay more for larger diameters. So the fixed cost in case of larger pipes is gonna be larger. And you can see here this plot is the fixed cost and the operating cost, the green and the blue lines, and the red is the summation of both, which is the total cost as a function of diameter. For larger diameters, we will go for or will need to pay more as fixed cost. However, for the smaller diameters, we're gonna pay less because we're not putting so much money on the hardware or the things that we are purchasing in the beginning. But in case of using smaller diameters, we will make the velocity larger because the area is smaller, and the larger velocity is gonna cause more losses, and these losses will require more energy to compensate these losses by adding or putting more power to the pump. So this is gonna be like one other thing that you have to take into account, that the operating cost for small diameters is gonna be large to like account for the losses that are gonna be taking place due to the small diameter and the high velocity, and it gets smaller as you go for larger diameters. So there is something that you are paying more here, and this is something that you're paying more here, and as you add both, you'll see that there is like a large value here, large value here, and there is a smaller or the minimum point here at some diameter. And this is what we want to find out. Where is this diameter that will produce the minimum total cost? Of course, this is calculated based on the lifetime of the project. So if, for instance, I'm doing this project for 10 years, or I wanted to go for 10 years, then I'm gonna do my calculations based on 10 years. And this is gonna be taken into account when we calculate the operating cost, and when we calculate the original cost or the fixed cost, we will divide it by 10 so that it's an annual cost, so that it works with the total cost. I mean with the operating cost. Finally, to calculate the costs for the fixed cost, we can calculate the cost of the pipes by multiplying the length of the pipe that we are going to use by the cost of unit length of the pipe. And the pump, we can find the energy or the pump head that's required from the pump from this equation, which is the Bernoulli equation or modified Bernoulli equation, but by rearranging it a little bit. And from this HP, we can find the power that we need to give to the pump in kilowatt hours or in horsepower, whatever, from rho g q h pump divided by eta, where eta is the pump efficiency. There are some other things that we can include, which is the size of the pump, which is different from like a case to another. So in case you need to provide more energy, then you might need to use a larger pump, which is going to be more expensive. This is something that we may include like in the second version of the calculations. I prefer to go for a simple case first, and then we can make it more complex one by one, so that we don't include like a lot of things in the very first time. So this is kind of all the points that I want to include in the introduction or in the revision. And in the next video, we will start the calculations using Microsoft Excel. So I'll see you then, inshallah. Goodbye.